That was a really wonderful talk. Thank you so much. Well, now I'm gonna bore you a little bit with the math, but hopefully the math is useful so that we can build foundation models for sequential decision making in general. Well, foundation model seems to be a buzzword. I'll tell you, what is very special about this foundation model my lab is building, and specifically be focused on world model based representation learning. So just a little bit background. I'm Furong Huang. I'm from computer science here at University of Maryland, and students are over there. So I do a lot of math, but my math is usually done in a way that is hopefully help me to build algorithms that can have guarantees, but also very useful in practice. So today I'll be showing you something that's, I'm personally really proud about in terms of what we are doing to make sure that things can apply in a variety of applications out there. So started. So we've seen a lot of success stories in machine learning and AI. So a lot of these success stories, however, has been in simulators, right? So, but when it comes to actual real world, there's a lot of complications and a lot of the assumptions that you make, or the stability you are seeing in simulators, or the things that you can expect in simulators will no longer exist. So as a result, we wanted to ask the question, are intelligent agents ready really for real world, sequential decision making problems? And in real world, there's a lot of challenge, right? So it's ever changing and data is really expensive to collect. It's not like you can just, automate your data collection in simulators. It's very expensive, really hard to train these so-called neural network agents, right? Policymaker, or, I don't mean to say policymaker, I just mean to say policy. Okay, so we have to deal with this unexpected changes. And this requires us to build agents that is intelligent enough so that it can adapt to these environment changes. Well, so my lab has been working quite a lot on this direction, right? So starting from changes in dynamics, most of the prior work have been focusing on that so far in the field. My work, our lab has been the first to study some kind of observation space change, in a sense that if you have infrared sensors, now you upgrade to camera sensors, how could you reuse your prior compute so that you can speed up your learning process and build an agent much faster? Right, so now moving on, we wanted to look at what is more practical and what is like the practical world that we're living, the actual challenges we're facing, which is almost everything changes. And in this case, we did some work, for example, reuse some of the samples in a smart way so that you could still reuse prior compute. But today, I wanted to show you some of the recent work my lab has been doing in terms of reusing a pre-trained representation. And essentially, representation just means that if you sensors are observing this very complex world, maybe as the form of images or maybe as a form of the videos, but at the end of the day, you're going to process them in a very compact space, maybe just the 512 vector, something like that. So we call this foundation models for sequential decision making in general. We wanted to indeed make it as general as possible to kind of get the idea of how much we can go in terms of building a generalist agent that can do a lot of things, just like a human being. So here is, the very famous foundation model picture here you will see everywhere. And I indeed just stole it on the internet. And what makes foundation model really unique is that it has a large size network, right? Oftentimes there's transformers, and this very large size network would have very diverse data that is fed to the network so that we train the network using very diverse data. For example, the data can be very multimodality, text, image, speech, sensor, 3D signals, you name it. And then after that, magically, really magically, like black magic, you're able to somehow get a really, really generalist, intelligent agent. We call it foundation models, such that it can actually adapt to a lot of tasks downstream, including question answering. And hopefully today, my goal is to convince you there is probably hope also to have an agent, a robotics agent, which is powered by a foundation model, and it's been able to do a lot of tasks downstream in terms of very low level manipulation. Okay, so of course, this is a transformer. I'm not gonna tell you nitty-gritty details of the transformer here, but I just wanted to let you know that transformers are really simple. They're just nothing but a bunch of multilinear operations and then some kind of nonlinear operation on top, and you stack them together. Nothing really fancy. However, transformers have been really, really successful in terms of building these foundation models. My take on this is transformer is not necessarily the magic, but rather how you train these transformers. In other words, how you use a mathematical objective such that you understand what the parameters of the transformer should be matters more. And that's why I'm talking about representation learning today. But now the question is, foundation model is so successful for natural language processing, as you know, right? ChatGPT, and even for vision tasks nowadays as well. But can you build foundation models for sequential decision making? It is tremendously much more difficult, right? It involves action. You have to actually do things. And we all know in robotics here that whatever you do, you basically can only do one action. That said, you cannot try out all the actions out there, right? So, and also the kind of feedback you're getting is so sparse and it's so much more difficult than just a natural language processing task. So can we build foundation models for sequential decision making in general? Of course, people try it. For example, back in 2021, now I say back in 2021, you just don't know how things are evolving so fast nowadays in machine learning AI, just hundreds of papers coming out every day on archive. And maybe 20K papers submitted to NeurIPS. Anyways, so back in 2021, you have this decision transformer, which is a first step towards understanding whether we can build foundation models, maybe using transformers. Okay, but then later on, Google also had this Gato, which is made a blast, essentially, right? Coming from DeepMind, it is a generalist kind of policy that can do a lot of things. But the performance are not very impressive. Not to the level that ChatGPT impressed people and they get 1 million users within 5 days. Well, so I wanted to ask the question, what makes good foundation models for sequential decision making? And I wanted to make a wish list here. First, I wanted to say it should be versatile, right? It should adapt to diverse downstream tasks and algorithms. It should be generalizable so that you can actually deal with unseen tasks and domains. And it should also be, very importantly, resilient in a sense that you can actually train things using low quality training data. This is quite important, right? So, your robots or even human or experts do not always give you very good kind of high quality demonstration data. Can you still utilize this kind of, robots wandering around and still know more about the world you live in? So my take on this is if you wanted to get being versatile, you probably wanted to go with reward free in a sense that, if you have conflicting objects, therefore you will have very different rewards. Your agent will get confused in terms of learning a general representation. So if you want it to be generalizable, I really think that the very important thing here is to build a world model on this latent space. And this world model is definitely not large language model that people have been talking about every day. Large language model is a world model. Sora, the video generator, is a world model. I think it is way, too far away from being a world model. A world model should definitely consider action. At robotics, we all know how hard it is to reverse engineer the actions it takes for the agent to do things on YouTube videos, right? If we can do that, then we've solved robotics, right? We have tons of cooking videos on YouTube. You can just reverse engineer the actions and you can just teach a robot those actions. But world model really should rely on actions. And I also believe that it shouldn't be relying on this very complex world we're living in, like very complex sensors. You have this sensor, you have that sensor, you have touch sensor, you have camera sensors. It should be in a compact latent space that is somehow incorporating all the modalities from all different sensors in the world out there. So that's my take on it. And then lastly, in order to have resilience, I think pre-training with very diverse data and very diverse tasks out there is quite important. And that's why I cannot emphasize more about the importance of data. However, there is a big caveat here that do we really need very high quality data in terms of demonstration or, like the expert demonstration, or can we just use low quality data as well? So that is a question I sort of wanted to ask, and we'll give you an answer for that. So this is a more technical slide. I'll just go through it very quickly. I really think that based on this wish list and based on our philosophy about what we believe should be the right direction to build a foundation model for sequential decision making, we should do pre-training. And we should really find a compact representation space. And that's what I'm, sort of advocating for, that you have this raw state and action spaces. You go through an encoder, you get a representation, and based on that representation, you can build a generalist policy or a universal world model. That's basically, laws of physics, something like that. Right? So what knowledge to transfer seems to be the key here. And today I want to advocate that you should transfer the representation and essentially keep the encoder there. So if you keep the encoder there, then you have new unseen tasks. You get a compact representation. Again, in the representation space that you know very well, you have a world model already. And then potentially you could adapt to downstream tasks by, for example, just fine-tune a policy hat on this very compact representation, right? So that's one way of doing it. Another way of doing it, again, you transfer this encoder, but you also just explicitly build a world model on this latent representation. You also reuse that world model. And in this case, I believe there is even hope for zero-shot planning, that you don't need to fine-tune any policy hat to achieve a foundation model. And that's really what we're hoping for. But anyway, to start, I wanted to introduce you a very recent work I did with my former PhD student who now has already graduated. We call it SMART. Basically, it's self-supervised multitask pre-training with control transformer. This is essentially the first general pre-training framework that achieved versatility, generalizability, as well as resilience. So very importantly, I want to highlight here that it's a very useful framework that is reward-free. And as a result, you can actually use very low quality data to train this generalist agent. The reason is that, think about it, we're trying to build a world model. As long as you learn a good representation, right? Like, you learned an encoder. On top of that representation, you're going to learn, given a state, given an action, where am I going? That is your world model. That is your transition dynamics. You don't really need high quality data to learn that. You could simply just set a random policy to let your agent wandering around and explore the world. And indeed, a random policy may be way better than a demonstration coming from an expert, because you would learn all the states. And that's very important. So as a result, I wanted to show you, as I mentioned, that representation is the key, right? But how, if people have been using transformers for all these kind of foundation models, but what is the good objective function in order to learn this representation? And in this first work, SMART, we propose this representation learning objective, which is called a control-centric pre-training objective. And it has 3 turns. I know it's slightly ugly, not very kind of unified and beautiful. It's not simple. It has 3 object turns. The first one is like a forward dynamics prediction, just predicting, taking an action, where am I going? And the second one, of course, is the backwards, inverse dynamics prediction. Not very surprising. But the most important thing is the third one, which is different from the first 2, which are only doing short-term control. You wanted to do long-term control. And indeed, that's the key why SMART was able to be successful in terms of generalizing. It does long-term control. Basically, it asks the question, what actions would you take to generate such a sequence when you're masking out these observation spaces? Okay. So, of course, there's a lot of details here, but the 3 objectives are really the key for SMART to be able to sort of, be in the first step of building a foundation model for sequential decision making. So some results. We did some experiments on DeepMind control suite, which, we used some kind of 5 environments, 5 tasks in the pre-training, and we test 10 tasks. So some of them are, already used in pre-training, but some of them have never been seen in pre-training steps. And you can see the result is actually pretty good. Well, first of all, it's amenable to multiple downstream learning scenarios, reinforcement learning, imitation learning. Those are the most 2 popular ones. It is also generalizable to unseen agents and tasks. Also, I think most important I wanted to highlight here is its resilience to low quality pre-training data. So your data collection can be really effortless. You don't have to hire a lot of data curators to sort of, do demonstrations. You can just let your agent do random policies to collect data. So I think that's really the highlight here. Well, SMART seems to be good, right? But however, SMART actually requires fine-tuning with very large number of demonstration during the downstream adaptation. So that is still pretty far away from what we really want as a foundation model that can 0-shot learn or adapt, right? It actually requires 50 shots, and each shot is 500 steps. So it's a lot of demonstration in the end. That's why we have this new work called Temporal Latent Action-Driven Contrastive Loss. It has a cute name called TACO, and the author is right here sitting in that table there. So TACO really is, I guess, the behind the scene, I'll tell you the story about TACO, and Regia probably can, tell you more about it. TACO is a mistake. It's sort of like a mistake, because he was trying a lot of these different things, and he found contrastive loss seems to work really well. And I will show you that the result is like 40% improvement compared with any state of the art. So we still don't know exactly why TACO works so well, but some conjectures here. First of all, it has this temporal action-driven aspect. It is not just one action. It has a sequence of action. In a sense, you are able to sort of like abstract the sequence of action into mini policies. I think that's what TACO really is doing internally. And second, I think it's also quite important, is this contrastive loss that people are using, which is very successful also in natural language processing tasks that people use contrastive loss. So in general, I think contrastive loss together with the sequence of actions is really the key for TACO to be so successful. I'll show you some results here. In DeepMind Control Suite, you can see TACO really achieved state of the art. Also, on the left-hand side, you see online visual RL. On the right hand, you see offline visual RL. So TACO really is basically significantly improving the state of the art. But this is not yet what we really are hoping for foundation model. We really want TACO to be applied to a lot of diverse tasks and being able to adapt to even more. right? So that's why we have this premium tackle. Actually, my colleagues are having problems. And they were saying like, why do you call it premium tackle? It sounds so incremental. It sounds like almost you're just making small modifications to tackle. But premium tackle is by no means just incremental. It has this very smart strategy of how to do contrastive loss using a very efficient way of sampling for negative examples. So what I mean by that, right? Previously in tackle, what we're doing is, you have this positive example, meaning like if you're at a state, you take a sequence of action, you land in another state, and that state is going to be the positive example. But everything else is going to be negative. But here, premium tackle is doing something really smart by saying, I don't want it to look at all these other things as negative. I just wanted to look at a small window around the positive example and just do one sample of it. And what that really is doing is you find the very hard negative example. The examples are very close to positive, but it's negative. So that information selection really helped tackle to scale to very kind of diverse pre-training and using academic setting with very limited GPUs, you're still able to do something to a pretty good scale. So show you some results here. Basically, this is like, again, showing like why premium tackle is different from tackle and how you can make premium tackle much more scalable than just the tackle. Here, we did try experiments on DeepMind Control Suite and Meta World. Actually, we also tried experiments on Libero, but I'm not showing it here. So you can see that we have some kind of pre-training and test split. And definitely, compare with Smart, what we're doing here is some of the pre-training tasks are simpler, whereas the test tasks are much harder. And this is really what we're hoping is some kind of like a thought experiment you would do for building like a smart agent that can generalize from easy to hard tasks. And that's what we're doing here. And you can see very impressively, premium tackle is like way better than any of the existing methods, including Smart. Okay, so you can see just using 20 shots in DeepMind Control Suite and 5 shots in Meta World, you're able to achieve really good performance in terms of generalizing to even new tasks. And what's even more, very surprisingly, the premium tackle representation generalizes to unseen embodiments. So something that you've never seen is a completely different agent, or it has very different action spaces, also generalizes there. And what's even more surprising to me is that premium tackle actually generalizes to unseen tasks with unseen views. So it's like, you get your sensors from this view in the training, but during test, you will have another view that the agent, the pre-training, has never seen before. It's still able to generalize. I think we're really getting closer to what the challenges we're facing in our real world application of robotics. So now, as I already kind of alluded to, that premium tackle can be used to fine-tune large-scale pre-trained visual encoders as well. Not very surprising, but I really like that premium tackle still is very resilient and sort of robust to low-quality pre-training data collection. So you could just let your agent wander around. You don't have to use a lot of demonstration, expert demonstration. You could still get a very good pre-trained visual encoder. So with that, I'll just say that all the work done by my students, the most important contributors are right there. Feel free to talk to them. And this is my group. Really fortunate to have a very kind of dedicated group, working towards our vision of building a trustworthy machine learning in an ever-changing world. Is that? Thank you.